Hello, everyone, and welcome. Thank you for joining us today. My name is Jelena, and I'm a project assistant here at Innocence, and we are part of the ELOQUENCE project. And as you may already know, ELOQUENCE is a Horizon Europe project that is trying to develop advanced voice and chatbot technologies that can transform unstructured conversations into interactions that are more understandable, safe, and unbiased. Through this work, we aim to create adaptable multilingual AI systems that reflect European values and that are especially safe in safety-critical contexts. And today's webinar is titled Building Trust in Machine Judgment. And in this session, we'll explore how AI systems can better understand human interactions and how can we design responses that are more accurate, transparent, and useful. Before we begin, just a quick note from my side. This session is being recorded and will be available on our website later this week. So feel free to drop your questions in the chat at any point, and we'll pick them up during the Webcafé discussion at the end of the session. And it's my pleasure to welcome today's speakers, Olda and Martin from Brno University of Technology. They are both actively involved in the ELOQUENCE project, working on difficult, if you ask me, different aspects of speech processing and improving the reliability of the AI systems. So rather than going into too much detail myself, I'll invite you, Olda and Martin, to introduce yourself and maybe give us a little insight of your work within ELOQUENCE, and then you can start your presentation.
Okay, yes, I will begin. Thank you, Jelena. I am Olda, and together with me there is Martin, and we will together show you some of the works that we are doing in the ELOQUENCE project in order to increase our trust in all AI systems that we are developing, and I will quickly introduce several topics that we will cover today. So, in order to build the trust, we strive to achieve this by improving the actual usability and reliability of the system. So we are trying to achieve this by enabling more streamlined and natural human-machine interaction that is not constrained. And we do this by enabling the speech input to the machine, and by taking speech directly instead of just text inputs, we comprehend speech beyond what can be just understood by transcribing it into words and then acting on those transcriptions. Later on, we would like to improve the system's answers so that the user feels comfortable using it, and we work on the techniques that identify what is important in the system's answer and why is it important, and also try to present it properly to the user. So these last two topics, this will be covered more by Martin in the second part of the talk. So first, enabling the speech input. This is quite straightforward. I don't probably need to explain it much more. It is much more convenient to speak to some assistant, to a system, and speak your mind, and also speak your kind of emotion or how you feel. It is much easier to express it in speech, and rather than write complicated sentences that when transcribed to text, the system would also have problems to understand. So you can see on this illustration that before you can type some complicated query into the system in the text form, you can just think and plainly speak to it, and you should get a answer either in a speech or the answer can be actually text. This doesn't need to be only speech, of course. We are working on speech, but in Eloquence, we were also working with the video modality in other work package. So this can be enabling audio-visual input. If you have audio and visual as well, you of course can get more cues out of the speech. And on this slide, you can see that there is a lots of information in the speech that we would like to grasp. So on the left side, what you can see is all of this information is kind of compressed in a standard cascaded system that would take this very information-rich input and simply transcribe it into the words. You will lose lots of the paralinguistic information. So this paralinguistic information that carries actually a lot in order to answer properly, most of it is being lost unless you somehow paraphrase it into the text, but then you lose the precise transcription. But what we do, we try to implicitly teach the system how to react on this. Of course, this is very complicated in terms of training data because we don't have annotations of this. So to solve all of this in a data-driven way, this requires more training, more data, but I think that this is worth it, of course. So these paralinguistic traits that we will be dealing with, not explicitly, but implicitly, they include cues like the prosody of your speech, the emotion of your speech, the all other aspects that are getting lost during the translation, and then the system is trained to provide you a proper answer. So on the right side, you can see that the internal states of the system, they kind of understand how you feel, if you are sure with your answer or if you feel stressed, and then provide you with a response that is more appropriate. And in this way, you can feel better talking to an AI system. Having skipped this this step of transcribing and then reacting to your input, it also decreases the latency. And latency is also something that is affecting the naturalness of the conversation very much and makes you feel better communicating with the system. So how do we achieve all this, and how do we build AI systems or models that can deal with the multimodal input? So first of all, the strategy that we used here is we like to leverage the existing foundation models that are built on top of different modalities, such as LLMs for text, some video models or picture models, and of course speech foundation models, and interconnect them. So these models are there for taking trained on rather simple tasks, like in LLM and speech. It can be trained on a similar concept of this language modeling, basically next token prediction, and this way we can save a lot of resources that are required to train these models. And of course, a lot of data, because to train it from scratch properly, it requires really a lot of computational power that will be out of our reach to really get something usable. And then when we want to interconnect them and actually use them together, we would like to be able to interconnect their internal representation so that the translation does happen in some information-rich space that is not as constrained as, for example, the immediate transcription from the speech to text. That is already a translation that is losing a lot of information. You can view it as a lossy compression that is really very effective, but you're losing a lot of information. That is indeed not necessary to get the core of the message, probably, but sometimes you're losing a lot. For example, in the case of stress or emotion. So in this slide, I have basically the core idea that we are using when developing systems like this. So on the left side, you can see some speech inputs. That's just a normal waveform, and that goes into a foundational model that is pre-trained on unannotated speech. So this is a model that just needs hundreds of thousands of speech. These models to the community, they are very well known based on this transformer architecture and some names. If you are in the field, this can be WAF-LM, this can be even encoders from a big ASR system, Hubert's, WAF2, and other systems such as this. These systems basically are trained to predict a piece of speech that that we mask during the training. So they kind of learn how to represent speech units, how to encode it very well. They are very well suited to be used as an encoders for an ASR system, a transcription system. But of course, in the middle of the system, they developed a very nice and compressed representation. And this representation of the speech can be translated to the space that we have in a large language model that understands the textual representation of our communication. So we just need to interconnect these two spaces. And we achieve this by yet another model, or in this case, much smaller, also a transformer model that is basically a neural network of several layers that is translating one representation space to the input representation of an LLM model. So this is a several 100,000 parameter models that is quite small. It needs to deal with several problems, like to subsample the frame-wise representation of speech, because we parameterize the speech every few tens of milliseconds, and we want to have a representation on the input side of the text large language model that corresponds to one token. What is a token? It's something. It's a unit that the large language model processes, and usually it represents to a word. So a word to let's say 50 millisecond of speech, you need to do some alignment. So this network also does this. It subsamples the speech representations and produces something that is closer to the frame rate of the tokens. And once we interconnect these two spaces, basically build a huge neural network, we can train it in a way as a normal neural network that is just larger. So for example, we can train it to just transcribe the speech, or we can train it also to do other tasks, like predict the dialogue states, predict the emotions, predict the search in a database, or any other task that you would imagine with a modern chatbot that used to be a text with a text input, and now is with a speech input. The objectives would be pretty much the same here. So on this slide, for example, there is just one example how we can adapt a standard retriever that search in a database of documents for a speech query. We would just take this architecture, this connector-based architecture, and align it with something that is text-based, basically train it to produce the same inputs as you would have with the text query, and enable it to ask the system with a speech query. So this is in a nutshell the technology that we have employed throughout the first 2 years of the ELOQUENCE, and built several models on top of it, published some papers. So if there are more questions about this, I can answer this later. And now I will pass the words to Martin, who will continue with information retriever and how to make these models more efficient.
Thank you, Olda. Hi, everyone. And once again, I'm Martin Fajčík, but luckily, thanks to the Zoom, you can see it on the screen. And I'm postdoc also here at BUT working on language. So today I'm going to discuss two projects we tackle in the ELOQUENCE, two kind of research directions we tackle in the ELOQUENCE. And the first one will be focusing on finding out what's important. But specifically, what we focus on are modern retrieval systems. The modern retrieval systems now can handle very, very long contexts. So we can index very, very long documents, but searching in very long documents can give us results which are also very long. We can get results for, let's say, 5 documents, which are pretty long, and we would like to either read them, which takes a lot of time, or we need to find what's important by, for instance, AI again. That's exactly where we come in, where me and my PhD student who sits right here, and you don't see him, have come up with the method for highlighting what's important in the text. I'm not sharing right now. Although you are still sharing. Are you going to switch slides or can I?
You can, I will stop sharing. Wait. Yes.
Okay, while Martin is trying to share his screen, I just want to remind everyone that you can type in your questions in the chat box, and I will read them later, or you can just ask them later on by audio. Yeah.
You see my screen, please.
Yes.
Okay. So we ended up right here where, well, we developed a method which is very fast and it's part of the retrieval. Well, specifically, let's go back to basics and to naive solutions which were applied 2 years ago, which typically was that we had a separate model for such a task. So we firstly had a query such as mission of the Voyager spacecraft, and we had a document collection, billions of documents. We apply the information retrieval models here, any kind of retrieval models, to get the desired results. Now, one of the components to highlight what is important was inputted then in 2024. So 2 years ago, that was already an LLM, which had to process all of the retrieved documents. So let's say 2 pages of results, 3 pages of results, and highlight what is important. One more technical question. Do you see also my mouse?
Yes.
Perfect. Okay. So moving on towards 2025 and 6, people have started to fuse this system, which highlights what is important, into the retrieval system. In 2025, there was a paper, not from us, there was a paper from Naver. We will fuse this functionality with the so-called re-ranker. Well, in fact, when you have a retrieval model, you tend to have in practice multiple stages. You have a first stage retrieval, which is applied to billions of documents. Then you have a second stage retrieval, which is applied, let's say, to thousands of documents. Sometimes you have even third stage of retrieval. So they applied it to the later stages. However, what we came up is how we can efficiently do this already in the first stage. So the outline of the idea is the following. In past couple of years, perhaps by past couple I mean from 2021, we typically train model by so-called distillation. The distillation is a process where we have 2 models and we try to train the smaller model or less performant model for some reason to perform as well as the often larger model or more performant model. So in our case, in retrieval, this tends to be the second stage retriever, which tends to be very efficient in terms of quality, but very inefficient in terms of speed. So we cannot really apply it to billions of documents, but we can use it for teaching a model which can be applied to billions of documents. So that's distillation. Now, what we do specifically is we actually add the extra learning branch. So traditionally, I will move one slide ahead. Traditionally, we will use the so-called document ranker based on cross-encoder architecture to obtain scores. This is a second stage retriever, to obtain scores for the first, second, third, fourth document for a given query, etc. Now these documents are pre-searched by some previous method, so we have some candidates, and we have scores of the so-called teacher model in distillation. However, we can also use a different teacher model as well. For instance, the LLM, which tends to work very well and have very high agreement with human judgments to judge which tokens, so which pieces of text, which parts of text are important. So we do that exactly, and this is actually our pioneering work. The past work was focusing always on large-scale provenances, never really on the token level. And now we design a novel distillation method to distill both things. The information about which document is important, which is the bottom branch, but also the distillation of which particular part of the document on level of tokens is important, which is the top branch. Here is an example from our system, which can assign a score of importance to every token in every document which is found. Here is an example of the bold part is what LLM actually highlighted. The red part is, or more red part means that our model was more confident in that. That's the important part of the document. Now, this is a nice example for the slide, but you keep in mind that in practice, we are interested especially in very long documents and applying this in very long documents where we really don't want to read all the contents. And what is really interesting, at least in our initial findings, which are already available in the preprint, is that this fine-grained Colbert architecture, which we trained, is very tiny. It has just 110 million of parameters, which is much smaller than the large language model. In fact, 245 larger is the model which we used as a teacher in this so-called distillation procedure. This small model on the right side, that's a so-called student model. Perhaps I haven't said that. So moving on, this is one of the first streams of work we are working on to figure out what's important in a very lightweight way, very scalable way in practice. And secondly, what we observed, and we were not the only ones, is that language models, they tend to work on the word token. They tend to work on token level. So if you ask them, for instance, if you are a programmer and you have code like in the blue part, in the white part, and you ask it to change what it prints, this is a C code for my fellow programmer here. If you ask it to change the hello world print to hello eloquence print, the model will start to generate token by token. Sure, comma, here is your function include blah, 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 right? And it goes on and it goes forward token by token. It will regenerate your text. And as it can cause error in every step. The more text is generated, the more likely it is that some error will appear. In fact, we can show that this error increases exponentially. So something like a double colon, which invalidates the whole program, can, in theory, appear. In practice, there are often different bugs. Now, what would be very nice is if the model instead would just copy what is same, change what needs to be changed, such as eloquence, and copy again what doesn't need to be changed. That way, there will be much less steps in which the model can make the error and make so-called error propagation. So this beautiful illustration, which we worked on yesterday, tries to illustrate exactly that. Let's build models which are not able to just generate tokens, but they can answer with provenance map. They can copy from what they've already seen before in their inputs. And they can glue it to the results. They can paste it so that we can firstly avoid the errors when the model tries to repeat something. And secondly, we can even trace from where the model took this information in the previous documents. Right, so they can switch between the generate mode and the copy mode and generate your required answer. Right, those are the two streams of work I wanted to introduce. Thank you for attention.
Thank you. Thank you both for your insightful presentations. So we now open the floor to questions from the audience. So feel free to drop your questions in the chat. We'll give it a couple of minutes. And while you do that, I'd like to start the Webcafé part of our session with my question. So how does moving from text to speech inputs change the way AI interprets user intent in practice? So you two
For all that.
decide.
Yeah. So maybe I can answer that. So it really depends on the application that we are talking about. So as we had in this illustration, one way would be to really detect the state of the speaker. I mean, for example, if he is stressed or not. So we are working in one of our project in a call center application for this emergency line services. And one of the crucial things there is to pre-sort or really alleviate the stress on the human operators and pass only the very difficult cases to a human operator, and those that, for example, are calling that there has been an accident somewhere, and there are like 5 similar calls happening for the one particular accident, that this can be solved by AI by a simple answer that the accident is already being taken care of. So in this case, we can understand from a caller that he is how much is he stressed, how much he is expecting some immediate and answer that is basically not being able to be done quickly by an AI assistant, because it is just the person is just not interested in talking with some chatbot when he is in a very stressful situation. So this way, this can be really rerouted to a human that would not need to be dealing with some people that just can interact freely with some chatbot because they are not in such a big stress. In other applications, this can be also very useful. Like if you search some large data and you're searching for, let's say, people from particular origin, or you are searching for documents that contain some paralinguistic information that you just get lost during the translation. Like if, for example, if you're looking for non-native speakers talking about some topics, this can be it. So it changes it this way that we can either pre-filter or we can utilize the information that we otherwise lost. Practically, it's still just emerging, because to really train with this data, one needs to have a large amount of it, and in research it is hard because the data sets that we have available are scarce. But I think in large scale applications, this is appearing more and more, and it will appear inherently when all of these traits are represented in the data and the systems are trained in an end-to-end fashion. This will start appearing naturally, that the system can kind of react appropriately given the emotional state of the speaker.
Thank you, Olda. So, as a kind of follow-up, maybe you can answer this as well. So, what are the biggest challenges when working with speech-based inputs across different languages and accents?
Right. So the challenges are mostly data related. So we have vast resources in English, and these the other, especially we call them low resource languages, we have a scarce data set. So there are of course some techniques how to overcome this. Lately, the augmentation methods, such as trying to utilize some text-to-speech systems to create some artificial speech data, are being used more and more. Of course, nothing beats the real data, but we are of course trying to work around this. And this is not only, of course, the amount of speech data, but the fact that we have different alphabets and different structures of the written text. But of course, with an advent of this large language model, this is mostly solved. The translation systems are working pretty well already, and I think text-wise, it is getting solved very fast, this multilinguality, but speech is basically hitting the data problem. Otherwise, I think this will come through as well as more data is being collected, or the methods to augment the existing smaller data sets are good enough to create at least usable baseline systems in these low resource languages, that people actually start using it. And as they start using it, we will have more real data. For example, I was almost always when I try to use any AI system, I speak to it in English, or write to it also in English, because it always gave me better results. But as more people start using it in their native language, because the baselines are getting better and better, it will be this chain effect or domino effect, that the more people use it, the better the data we have, and then it will be even better.
Okay, thank you, Olda. So we got a couple of questions in the chat box. So, which of the techniques you have developed in Eloquence do you see could be adopted in the real world?
Can I try this one?
Yeah, sure.
So, well, none of the techniques we have developed are purely theoretical. All of them have working systems. Now, some are still requiring a lot of tweaking. So we are mitigating the gap between what is the best out there and what is our system. For instance, well, let's start from the end. The copy-aware language model is very efficient. It can copy very big chunks of text in single step. But the problem is that, well, it can make more errors. There is always some errors. So it's efficient in terms of speed, but not in terms of performance, which in future, as the models are growing further and further, might be less of the issue, and speed might become more of the problem. Now secondly, if we move towards the highlighting, was important in the text directly from the system which does the search, directly from the retriever. Well, actually, right now we are matching what LLMs are doing. We cannot distinguish by humans, what was done by LLM, and what was done by the retrieval system. So, well, if we won't hit during the paper preparation now some more challenging situations, or someone else will point out them, this is actually a technology which seems to be ready, which seems to be actually ready to be applied out of box in companies out there. Perhaps Olda, you can comment on the speech technologies we've created.
Yeah, the speech technologies. I think the systems that I highlighted about interconnecting speech to an LLM, many of the current very good ASR systems are basically employing similar techniques, making speech transcription interconnected via some encoder to a powerful LLM system and train it in this end-to-end fashion. So this is already happening. The other applications like speech-enabled search or question answering system or something like that. This is applicable already now as well. If one wants to build such a system with lower resources. I don't know if it is actually being used in some commercial products, but this branch of research is also, of course, also competing with a totally end-to-end system that would be trained from scratch from speech. Like companies like Meta, Google, Microsoft, they had millions or even more hours of speech that they train on, and practically infinite resources to train on. And there is a completely new or the emerging branch of research trying to directly train the model that is not composed out of several foundation models, but trained directly from scratch to a target application. So we will need to see which approach will win, but of course this kind of massive data and resource approach that these companies can take, this we cannot replicate by training it from scratch. We can create many like niche use cases for many applications where the speech input is needed, and there it is very useful to interconnect some specialized models or some specialized modalities together to create a good application, while something that is totally massive, like let's say speech transcription, the future will most likely be that this is trained in a completely end-to-end fashion, or even a dialogue system, most likely, like speech language models are emerging to be very, very successful, or speech codecs and so on. So time will tell to which applications will more or less leverage interconnection of more general large pre-trained models, and which ones will be trained in a compact way with a huge amounts of data and huge model parameters. By compact way, I wanted to say like in a unified model architecture, not something stitched together via these connector modules. And I think that's it about the speech.
Understood. So we have one more question from our audience. How can AI systems show users why they made a certain judgment, especially when the input comes from the speech and may include uncertainty, emotion, or missing context?
Yeah, so this is like something split between me and Martin, but maybe Martin can try to address it.
Well, like I can try how we do it, especially in text, right? And then we can brainstorm what of these are transferable for speech. So in text, there is no one size fits all. Like sometimes the decision can be explained by providing a document or a text or a part of information from which the language model have took this information, right? This is called grounding. We ground the information by some the response by some information. Sometimes you just need to ask the system and it can elaborate further. That's a natural way also how humans communicate within their society. And it is a natural way of obtaining more information about the judgment, which is interpretable to humans. But if we are seeking the interpretation of why the language model has made the decision it made, why it says it's white when you see it blue, well, then we need to have more technical experience. There is a part of our lab which works in interpretability. And some of the techniques of interpretability can identify the features existing in neural networks. So for instance, they can say that, well, there is a detection pattern that if there are three eyes in the particular image, it's unlikely that it's a cat when the detector detected three eyes. But if it's two eyes and tail, well, there is a particle neuron which activates when it sees two eyes and the tail. And in reality, in language, it tends to be a combination of multiple signals, but still it can be at least partially explained that, well, this decision came because there was this word and this word, and I found this and this, and at the same time, I found this and that. So it is really hard to explain it to user who has no previous experience, but we can trace back to see what kind of patterns were recognized by the model when the model said white instead of blue. How this can be transferred to speech? I believe it's similar, right? Olda, could you?
Yeah, I think pretty much the same way. Of course, the model knows its input. It has multiple capabilities. The modern systems are trained with multiple tasks in hand, and not only it can give you the answer that you are concretely asking it to do, but internally it also answers many other questions that about the input that it has been trained on. So it will determine, for example, the stress level. If the system was trained on it, it will determine the language, the dialect. It determines whether you are speaking English natively or non-natively, and so on. And these answers can be somewhere stored internally, and you can also ask about it during some investigation. Why do you think that the answer was done like this? Of course, this implicates that part of the model or some of the data during the training were annotated with respect to all of these traits, and some of it the system just learns intrinsically through the data, and it is actually very hard to explain it. But with these larger AI assistants that are built on top of this systems that are instruction tuned, meaning instruction is a different application, so it internally can answer many questions about the data internally. This is what we can do: investigate it by answering multiple questions about the input data that could just the model can elaborate on what it had on the input rather than only just spitting out the answer to your original question.
Okay, thank you. If there are no other questions from our audience, we can conclude our sessions. So thank you once again, Olda and Martin, for this very insightful discussion. Like always, I learned quite a lot talking with you, and thank you to everyone who joined us today. So this webinar, like I said, will be available on our ELOQUENCE YouTube channel and social media. So make sure to follow us and stay tuned for more updates of our upcoming events. So thanks again and have a great rest of the day.
Thank you for inviting us. Bye-bye.
Have a nice day.
Thank you all. Bye.
Thank you all. Bye.
Bye-bye.